So this is lecture 17 by Harvey Friedman on invariant maximality derivations. Please.
Thank you. Okay, so this section 3.8 is the absolute heart of the derivation side. And I'm reworking it and getting some more refined material, and it's well under control, but it's still a little rough. So you will find today that I didn't get a chance to format some of the stuff, but it won't be too difficult to see what I'm doing. So I ran out of some time, but I think it deserves three parts. I think if I just gave one more, it wouldn't. There would be some loose ends needed. And beyond 3.8, there will be uh, some stronger results about more general derivations. By derivations, I mean I'm proving that various things are fully usable. Various functions are fully usable. And there's nothing but full usability going on in the derivation side of things. But these weaker kinds of usability, full usability, and also I restrict the dimension. Yeah. So there's full K usability in this 3.8. And the uh, other kinds of usability that are weaker, uh, that's in the reversal section that we did. So in other words, the weakest of all was reversed. So, and that's the best situation. All right, so let's continue here. I already started some stuff, as you know, I already started 3.8 a little bit already last time, but things are going to get reworked in a sense that you will see. All right. 3.1, 3.7 are pretty polished. And I keep changing the name of the book. So now the current name of the book is Invariant Maximality, Finite Free Choice, and Finite Games. May change again when we get into, so after this chapter 3, having chapter 4 under our belts, we're going to go into chapter 5, which is the finite free choice stuff. And I expect some additional improvements on the full naturality of the explicitly pi01 form. All right. The table of contents of this chapter 3 has been changed a little bit, particularly in the section we're talking about, 3.8. But this hasn't changed. All this introductory material. With what is usability, one usability, and so forth. The finite usability is now on the downloadable page. That's section 3.6. That's a hefty section. That's quite elaborate. And I had to do some serious reworking to make that clearer. But we understand exactly what finite functions can be fully used. And that's the same as being weakly usable, meaning, let's say, two usable. One usable is a special thing that is completely analyzed and which shares nothing, is a kind of a trivial a comparatively trivial situation, to usability, all the way up to full usability are all the same for finite functions. We already did this stuff about introducing finite introduction to infinite usability. Actually, that's been upgraded and perfected. Also, in the downloadable manuscripts, you'll find 3.7 has been updated and perfected. Basically, there are two approaches, if you remember, to infinite usability. One is to use almost identities, which is just identity function, finite function, and the other is to use order theoretic functions. Or every order theoretic function turns out to be an almost identity, where the identity part is on a finite union of intervals. Almost identities are more general, but the important case of almost identities is when the almost identity is on a union of rational intervals. And then the two notions coincide. This is discussed in here. The two notions coincide for our purposes. Our purposes mean strictly increasing functions, because strictly increasing functions is an overriding necessary condition for usability, or even the weak forms of usability. All right, now it's 3.8 that's at the heart of this section. Is the heart of the section, and this is what I think needs two more lectures after this one to really do everything perfectly. And this one is trivial because it's just a case of finite function. We already discussed this. This is a new section which I took quite a bit of work to write. And this is the one master construction, so that not only does it take care of this is the main climax. Not only does it take care of this, but it's also one main construction which takes care of doing other things like this and this and this. Although this one doesn't need a lot of this doesn't need too much of the critical construction. So today we're just going to go through 3.8.5. We're going through this. This one I couldn't put together quick enough. There's some interesting issues. I know it looks similar, but there's a difference because 0 is the right endpoint of the interval, and here it's separated. This makes a difference. Now, when you put it all together, you get this. Okay, so we're just going to do this today. And then the lecture next time will be essentially at least this, and maybe some of this, and then there's some cleanup stuff about this. And also, I'm in the process of making some more precise statements about what happens in the dimensions. So there's a good 3 lectures here, this being the first one on this 3.8. Exactly the contents of 3.9 and beyond are a little bit in flux. There's so many open issues that I don't understand yet, so I don't quite know what the scope is. By the way, I'm not 100% sure. I've done these calculations before, but maybe in a slightly different notations, whether this is min k minus 1, n minus 1, or something slightly different. It's something like this, and this is subtle cardinal. So Yeah, maybe I should possibly write this in the title because I am fixing K. See, I fixed 2 here. This is okay. Yeah. All right. And I think it's important to highlight the omega 1 case. This, I think this is, we talked about this before. All right. So um, this is important because the statement that we actually reversed in section 4, that is 3.4, the four set, no, chapter 4, I'm sorry, chapter 4, what we did all those lectures on uh, uh, is actually has only one variable, k equals n. And in this section, we prove, among other things, or we actually mostly that, if I remember, maybe some other things, is that that weak form is actually equivalent to that is when k equals n is actually equivalent to these stronger forms. But the particular one that we reverse is actually a highlighted item in 3-point question mark, is explicitly discussed in there. All right. So now we've have given a clear, necessary, and sufficient condition for usability of the finite case within CIFA, that is super exponential function arithmetic. We turn to the infinite f. Now, obviously, every identity function is fully usable because f is the. Okay, I think that this was not meant to be here, simply because it's really an introduction to section 3.7 and not 3.8. It's really a comment on 3.7. All right, so now we're going to start. And this is all review that we did. What these functions are. They were already used in chapter 2 when we did just some core math. But we did it there with the real numbers, and now we just use rationals. But you could actually avoid doing that because you can use because we only use rationals in the application. So that's an expositional matter. But officially, we're just going to say that these functions now are declared to be purely rational functions when they used to be real functions. And these are the definitions that we know you've discussed a lot. Oh, and we don't put the Q here. We don't put the Q here anymore because it's understood that this is just rational intervals all over here. All right. All right, this gives some preview of what is in 3.8, but so that's nothing. All right. Now this we already discussed. This is a finite function, and it's covered that it's fully usable. You need Ramsey's theorem in every dimension, so it's CIFA. CIFA is equivalent to Ramsey's theorem in every dimension plus EFA. Okay. Now, this is a new chapter, and I like this approach the best. I may have the master construction, and then, in other words, there's this master construction for handling this usability here. And it doesn't quite do anything. It needs a dose of set theory. It needs some set theoretic combinatorics to get the usability out. But it's the general framework for injecting the needed set theory that's used. In other words, it's a setup where the issue becomes what combinatorics am I going to apply to it in order to get what kind of usability out. So the more set theory you have, the stronger the usability conclusions. That's the setup. That's the general way of doing this. Um, okay, so this is the this is infrastructure. This is the infrastructure for the core of the invariant maximality derivations, the core of this. Okay, so and it's all couched in terms of set theory. It's couched one of the things I'm going to do in the third lecture on this section is say more about the formal systems that these things, uh, uh, what base theories will this work with? But as we just do it uncritically, the base theory is ZFC minus power set, and this is the a base theory that we use, and of course we add to it to prove things. That's the point. It's not enough to do anything interesting as far as as far as I know, it's not quite enough to do something interesting. It's right on the fence. But it's the base theory for which I can describe everything. All right. So I'm going to be talking about ordinals all the time here and ON. So, it's the usual informal thing that you can use fake proper classes because you're working in ZFC. You can talk about the ordinals. You don't have to have the class of ordinals as a serious entity. You don't have to do that. Otherwise, I'd have to go to a class theory. I'd rather just think of it as ZFC minus power set. So let alpha be any ordinal. We have the space T alpha equals alpha plus 1 cross 0, 1. I used to break that up into a union of singleton alpha cross. But this is clearer. This I like better, just to say it that way. And less than star is the lexicographic order on ON cross omega. All right. So alpha P is less than star beta Q if and only if blah, right? We also need to fix forever some effective, it doesn't make any difference which one, an effective 1-1 enumeration of the rational numbers 0 from 0 to 1. It has to be 1-to-1 enumeration, and it has to start with 0. It has to start with 0. That's fixed. And we use that in order to create a well ordering, because less than star is a dense linear ordering, less than double star is a well ordering. It's given by either alpha is less than beta or I is less than J. These are the rationals in here. Okay. So we have a vitally important dense linear ordering and a vitally important well ordering associated with it, so to speak. And then less the double star gets extended to any Cartesian power of ON cross omega by this lexicographic lex max process. In other words, you're less than if and only if first your maxes are less than. Um, oh, yeah. These points are in ON cross omega, so I have to say less than star. Yeah. But actually, that's not what I meant. I think this is important that I fix that. Yeah, yeah, that was a mistake. Yeah, less than double star max, or the maxes are the same and is lexicographically lower. Lexicographically lower according to double star. So less than double star is the only important thing in here in one dimension. It's lifted to k dimensional, so to speak. All right, and now I like to use the slash notation. So less than star slash T alpha. So this lemma, although it's not directly, I don't track how it's used. it fixes all the notions, because if you read this lemma and it makes sense to you, you actually know all the definitions. So this is a dense linear ordering. So when I restrict, so I actually, the way I set this up, I like to restrict to the actual set. So this seems to be wrong. It seems to be like this. So less than star slash T alpha squared is a dense linear ordering with left endpoint 0, 0 and right endpoint alpha 0. You see the setup. And is not a well ordering, of course. And less than double star has the same left endpoint and the same right endpoint. That's important, see? And this is so I think we need to fix this. This is a well ordering. I don't see why this period is here. Oh, yeah. No, sorry. It's part of that sentence. So now I know why that period is there. That's fine. Less than double star restricted to T alpha K is a well ordering on T alpha K with left endpoint blah and right endpoint blah. Okay, and now the set of all beta comma 0, this is important. Set of all beta 0 such that beta is less than or equal to alpha plus 1 is a closed set in less than double star slash T alpha with greatest element. That greatest element is here. Well, no, its greatest element is alpha comma 0. Yeah. Yeah, alpha comma 0. This is a one-dimensional factor. Okay. You see, having that 0 is the first one of the p's in that effective enumeration of 0, 1 makes this a closed set. Now, if I have an order invariant, this notion of order invariance we even had a chapter on, so to speak. All right. This notion of order invariance is clear, but we want to transfer it to transfinite space. We need to transfer it. This is one of the key ideas in the whole subject, is that you lift these problems, that are in the rationals on, you lift them to various giant well-ordered systems, or linearly ordered systems. Sorry, linearly ordered systems. They're yeah, not the other so as much. Yeah, just these. Okay, so E star is just this. Is the lifting to ON cross 0, 1 from -1, 1. And it's a lifting. I mean, it's a side lifting. It doesn't include -1, 1, of course. The whole point is you're lifting according to the ordering. See, this notion of order invariance is dependent on the ordinary less than, and this notion is dependent on less than star. Yeah. Okay. So next, next is the crucial definition of the greed. There's a master transfinite greed construction, and this is the essence of why I want this to be a special section on the essential constructions, because I want to make one greedy transfinite construction, and then build on that, pieces of it, and then use pieces of it according to the large cardinal combinatorics. You see, and then and then isomorphic and the countable systems and isomorph them to uh, to the rationals and thereby prove the usability. Okay, so this should be inclusion. Let's do that. Yeah, but I didn't there's a lot not formatted here. I just ran out of time. All right, so a subset of ONK it's defined as follows. X is in S if and only if you could put we're trying to build a subset of E star. We're trying to build a k-dimensional object whose rth power is contained in E star, the constraint. The E star is the constraint. And so we want to put X in just in case if we take what we've done up to now, in other words, S restricted to less than or equal to less than double star X. Well, I guess I said that I was going to put the whole thing in if I did a restriction. All right. I said so, I'll do it. All right. S restricted to this union singleton X, is it any good? If it's any good, then we put X and S. Okay. So it's greedy. So if you can put it in, fine. Okay. This is the greedy condition on S. And if E is ordered invariant, S is explicitly uniquely defined in ZFC. So we're still avoiding class theory. We're still avoiding class theory. Because it's the usual thing. You just define this transfinitely, and then you take the virtual union. All right. Standard stuff. Now, 3823. So E is order invariant and kappa is an uncountable regular cardinal. Now, uncountable regular cardinals, omega 1 being the least one, play an essential role in this and just about anything in set theory that's going on. Now, we take the elementary substructures. We take the elementary substructures which have no gaps. In other words, they're the form alpha 0, 1 union kappa 0. I want to consider the structures with both less than star and less than double star as relations. And I don't want to have to put the domain down. It's just awful. So when I'm in a structure and when I'm in certain contexts, I'm allowed to just write restricted. So if I'm writing a structure, I'm allowed to put this restricted sign to mean implicitly that I'm restricting to the domain squared, say, or the domain to the kth power. See, this is the right way to do this. If you don't have the restricted signs, it's not quite true, although nobody cares. And if you do put the restricted sign and then you put this thing, it's just impossible to read. It's so long. So I think this is the happy medium. So when is this an elementary substructure? See, it has no gaps, but it does have this top point. You see, you can't get an elementary substructure without having the top point. But you can have the top point and have various things underneath. Okay, so you look at the set of all alphas such that this is an elementary substructure, and that's closed unbounded. It's a closed unbounded set of limit ordinals less than kappa. All right. And that's pretty straightforward, standard stuff. Union of substructures is a substructure, so that's why it's closed. Now, for it to be unbounded, you actually have to build something. And you use the uncountable regularity to show that you can do that. Uh, all right. So let E be order invariant and kappa be an uncountable regular cardinal. For alpha less than or equal to kappa, lambda sub alpha. So I didn't this is lambda sub alpha. I didn't format anything. Lambda sub alpha is the alpha element of the closed unbounded set given by the previous lemma. See, so we want to enumerate this. And in particular, the top one is lambda sub kappa, right? Which is just kappa. All right. For alpha less than or equal to beta, we have uh, we define an embedding. This is an important idea, embedding. Namely, it's called pi alpha beta, and it goes from T alpha to T beta, and it's the identity on alpha cross 0, 1, and it maps, now it's one dimensional, it maps T of alpha 0 to beta 0. See, it's the jump. It's a jump of the tops, the top to the top one. Okay. And we're going to use that because it's going to be used, it and its inverse are used as isomorphisms, you see? So let E be order invariant and kappa be an uncountable regular cardinal, then for all alpha less than kappa, a pi of lambda alpha kappa is an isomorphism from T of lambda alpha less than restricted, from the structure, from this structure, onto the higher structure. Uh, yeah. Now wait a minute. Is this what I wanted to say? Yeah, that one's an isomorphism from there onto, yeah. Right. Because this is the one that goes to kappa. This is the one that goes to kappa. So this says that that if you jump them up, you get an isomorphism. If you jump up from alpha to kappa, you get an isomorphism from the structure with alpha to the structure with kappa. Okay. And the reason is that if you take lambda alpha, the target structure, lambda alpha union kappa 0, the target structure, uh, it is an elementary substructure by construction, and therefore it satisfies the same sentences, and therefore it satisfies the sentence uh, uh, that S is greedy. It satisfies that S is greedy because the full structure satisfies that S is greedy. Okay. So pi of lambda alpha kappa is an isomorphism H from T lambda alpha from this structure onto this structure. And because H was given by transfinite recursion and less than double stars of well ordering, we have H of S equals S. H of S restricted equals S restricted. Okay. All right. Now, this just says that this is true when you go from alpha to beta. But suppose alpha is less than beta is less than or equal to kappa, then if you take this pi map from lambda alpha to lambda beta, that's an isomorphism from the structure on alpha onto the structure on it's not, it's into. Yeah, into. Yeah. And also it preserves maximality that that has nothing to do with the second beta. This is always maximal with respect to being in E star. You see, that's because it's a greedy construction. It's maximal, but if it's greedy, it's going to be greedy at every stage, so to speak. And these T spaces are initial segments of less than double star. Now, it'll be convenient to break down theorem 3825 into its basics. In other words, get rid of the notion of isomorphism. So let E be order invariant and kappa be an uncountable regular cardinal, and let alpha be less than beta less than or equal to kappa. And we summarize what we need to know. If I have k elements less than or equal star lambda alpha 0, lambda sub alpha 0, and if I have delta 1 through delta k be the result of replacing each lambda alpha 0 by lambda beta 0. You see? We replace one top guy by the other top guy, then you don't change membership in S. Then you keep the membership in S the same. That's a way of unraveling everything because the isomorphisms were so simple. They were like moving these single points. And you notice that this is quite close in spirit to, except it's in the transfinite, to invariance with respect to these functions we're playing with that we're trying to show usable. You know, they were defined by replacing, making replacements. Okay, so, and this is actually stronger than what's embodied in the functions we're trying to show usable, because then we only do, remember, we only go from one thing to the next. It's only a shift. Those things only talk about shifting, whereas this is more general. Yeah, but in a way, it's still very similar because we're just going by one. You see, what's happening here it goes like this. Those things we're trying to show usable say that you can have multiple lambda alpha's zeros. You can have multiple ones, and then the idea is you want to move them all and preserve membership in S. Here, we're setting up the infrastructure. We only can move one. So we're only moving one as opposed to needing to move more when we actually get into the usability. Okay, that's important to say. And the other side of it is, so one side is this invariance type thing, very special kind variance type thing, and the other is the maximality. So invariant maximality. So here's the maximality. If I take S restricted to the space T lambda alpha, and I guess I'm going to have to do a square because I said I'd do that. No, that should be K, not square. There. Is maximal with the fact that the rth power goes in here. So this is a constraint. That's the constraint. So we actually always have this. We have it at kappa, but we also have it anywhere else, anywhere below kappa as well, that we have maximality all over the place. And we have this this moving of just one indiscernible. We have moving of one indiscernible. I'll say this better, in the final form on the downloadable manuscript page. This is moving the indiscernibles one at a time, and this is having a maximality at every level. Okay, that's what they are. All right, now we're ready to apply this machinery. So the first application is that -1, 0, 0, 1 is usable. And we have to we're going to use omega 1. So we give a proof that this is fully usable in ZFC minus power set plus omega 1 exists. We don't know how to do it in ZFC minus power set. Okay. So we fix K and R in order invariant E, and we apply this last thing, infrastructure thing we did with E and with the dimension being 2. This is no, K equals no. Not K equals 2. That's the next section. Sorry. And kappa equals omega 1 to the ordinal omega 1. And alpha equals 0 and beta equals omega 1. Right? Okay, so what do we get from the previous transfinite statement? Let these be less than or equal star lambda 0, 0. Let delta be another one, which is the result of replacing each lambda 0, 0 by omega 1, 0. All right, that's what this says. Then if you do that, you wind up with the same truth value in S. Right. Okay. So, and the second thing is the maximality. Just the one maximality for omega 1. See, we don't need too much to do this. We don't need too much to do this. We just do this on omega 1. Remember, it was true at all the other places. And this one we do below lambda zero. And this is just a single replacement. All right. Now we take a countable substructure, D less than D, B, C, D, S prime, elementary equivalent to the structure, the master structure we've been using here. T of omega 1 less than star. That's the ordering, the basic ordering. 0, 0, lambda 0, 0, omega 1, 0, S. S restricted. Clearly D is greater than 1, and less than D is a dense linear ordering with left endpoint B, right endpoint D, and B is less than C less than 1. All right, now we can go, and C is in between. Now we can actually go further, so C is in between. These two are the endpoints. Now we can go further and take, yeah, and S prime is going to have the maximality, right? And we can go further and take the make sure the copy is, D is just, the domain is minus 1, 1, and it's just regular less than, right? Do this. And then the left endpoint is minus 1, the right endpoint is 1. Uh, See, I think I mixed two sections. This is the section on uh, yeah. So this is I'm mixing it with the other section. I think that this is what I'm doing. Okay, by elementary equivalence, this becomes this, let P1 and P2 PK less than or equal to 0. So I'm just translating all this because of the elementary equivalence. Replacing each 0 by 1, then P1 through PK is an S double star. So this is the same thing, except that I've isomorphed it to this. And so also I get this is invariant, because that's what this means, right? That's what what the invariance means. And then I get this is maximal with respect to this. And 2 is just a rewriting of 1. Okay, so we have just completed the proof that that this is fully usable by using the infrastructure, that machinery, in order to set it up, in order to pluck out what we need. So we use this this thing here. This thing here we used. Okay. All right. So we just did one of them. Oh, yeah, yeah. Now this is the other one. This one we have to cut down the dimension. See, before the dimension was arbitrary. Now we have to cut down the dimension here. That's what this colon 2 means. So the minus 1, 0, 0, 1 is like having two indiscernibles in arbitrary dimension. We saw that having omega 1 is sufficient. Here we allow any number of indiscernibles, but restrict the dimension to k equals 2. And we again see that omega 1 is sufficient. So how do we do this? We apply this theorem we're talking about, this delicious theorem with kappa equals omega 1 and alpha in omega, so we get this. This is all we need from that statement, that if I have two pairs, remember we're in dimension 2. If I have two pairs, and I have another two pairs which result in replacing each lambda I0 by lambda J0, then this one, these two are in S as a pair, if and only if these two are pair. Yeah, so I guess this is what I have to say. If only this pair is an S. And then we do want to know that we have maximality for every one of these, uh, we're in dimension 2, aren't we? Yeah, I got this. I have to be careful about this. I check it carefully. All right. So we have the maximality, but we need it for all. So we're going to use omega of these levels before we just use two levels. We're going to use omega of these levels. Actually, sounds like that's more than what we want, but more than what we need. But there's a reason you have to do that. And remember, we're just moving one at a time. We're just moving one of these indiscernibles at a time here. This is important. So we now take a countable substructure. This time with infinitely many of these. And this is elementary equivalent to this structure. And we just take an isomorphic copy. So we finally get down to this structure by elementary equivalence, and then we have this as a restatement. Remember, we're only moving one at a time. See, so this is all we get, one at a time. We're not moving two. The problem is, what happens if I have, say, A5 comma A7? There's all bets are off. I don't have that. And then I have the maximality. Here's the maximality for each AI. So we don't have quite what we want, but we can get around it. We can use the infinite Ramsey theorem to cut back these A's, so that with any pair of the same order type, we have if and only if, even the same order type, not just shifting. That's because of Ramsey's theorem for pairs. It's now clear that if X and Y are in there in the cutback, and Y is the result of replacing each coordinate Bj in X by Bj plus 1, then we don't change. Because we already have it before that we can move any one. Now we can move any two. We're home free. So we then have the invariance that we're looking for. Now we also have the maximality, and that is that we also have the maximality. And now we have to worry about what the right endpoint is. See, we're going to change this. The actual right endpoint is 1. The 1 is worthless. So what we do is we just cut it off. We make sure the structure is just cut off at one of these indiscernibles. Maybe, and you want it to be the nth one, actually. You want to have n of these, you see. And you want to cut the structure off and still keep it invariant. And the reason that's true is because we have this strong kind of invariance up to any place already before. All right. I'm going to have to go on a little bit longer. This one, in a way, is a little bit easier once you believe in Erdős-Radó theorem. So this one that you can now we're going to handle multiple ones, but any number of dimensions. We just handle this kind of thing even with more, with 0n, if there's only 2 dimensions. But if there's any number of dimensions, we were only before handling 0 and 1. Now we're going to handle any of these and in any number of dimensions, but we're going to have a cheat. The cheat is that there's a gap between 0 and the first indiscernible. Then we need Z. By the way, if this thing was a 0, then we need SRP plus to do this, and we reversed it. We already know that we need large cardinals. If that one is a 0, we need large cardinals. So with this gap, though, we can do it in Z. And this is the Bethe numbers, iterated exponentiation. This is the statement of Erdős-Radó. This is Erdős-Radó statement which is best possible in the appropriate sense. Okay, this is Erdős-Radó. Here it is. Okay, so now we're ready to prove this. And we apply that master statement from the infrastructure with E and the cardinal kappa, which is this iterated exponential at omega plus. And let alpha be less than kappa. We have, all we need is the maximality. This transfer stuff by points, we're not even going to use to do this. So everything's easier. But there's some combinatorial coding that is standard that has to be handled. Now we claim that there's an A. So we have these lambda alphas where alpha is less than kappa. We can find an A of order type omega such that the following holds: if X and Y are in A union this stuff in here, where X, oh yeah, if X and Y are in A with indiscernibles with only these parameters. You see, we're only going to use parameters way below. You see, we're only going to use these parameters. We can get away with just using these because of the gap. See, the gap between 0 and 1 over n. And we're preparing something up to isomorphism. See? So we form the structure 0, 0, 1, 0, lambda 0, 0. Yeah, this 1 is really small. We're still in the transfinite case. Together with all these indiscernibles, together with the last one. And we take an elementary substructure. So we eventually get something like this. Here we are, sorry. We get something like this where E is the right endpoint, B is the left endpoint. C is just, it used to be like 1. C is just some number sitting here. I don't really care what. And these are the indiscernibles, you see? And then we can get an isomorphic copy -1, 1, because any countable dense linear ordering, it looks like that. with the intervals and then one on top. And then we can cut off at AN. Because if we cut off at AN, we get this. We get that kind of invariance. And then we make an isomorphic copy here, fixing 0. All right. 0 is fixed when we made the isomorphism from here to here. Okay, because you can move these around and keep this little one. So we didn't really use the full power of that infrastructure thing, because we didn't use that you can move a single point, the single top points. We did very much need that in the other two derivations, but not in this one. But this one needed another ingredient, and that was the Erdős-Radó theorem. Now, when we get to the big one that requires large cardinals, we'll do something like this, but the large cardinal combinatorics won't be Erdős-Radó. It will be the subtle cardinal combinatorics, or the SRP combinatorics. Okay, so I think that I went over a little bit, but I think that this is what I wanted to say. Yeah, so I'll get this formatted and cleaned up and everything, and we'll be set to go for part 2. Part 2 is this here. We start with this one, where we don't have a gap, but we created a gap at the end. So this is a little bit of a tricky business. We created the gap at the end, but we didn't have the gap in the front. And it turns out you can still do this with Erdős-Radó. You have a little trickier, but you can still do this with Erdős-Radó. And then we can go do this one, which is, of course, the main event. And then we want to break it down. We want to get some more precise information also. Yeah. Okay, so I think that, okay, Andreas, I'm done.